Okay. Let me go and get started. I think. Hopefully. Um, so. All right. So let me get started. Let's see where we're at. So first of all, yeah, I've gotten a little bit behind. I think in this class I'm not too bad. So I am still working on the most recent assignment that was due on Friday. So I'll try and get those back. Um, so yeah.
What was assignment?
Right, Sign 5, right, on the support vector machine. So I haven't returned those back yet, but hopefully I'll get those worked on. We can maybe discuss that a little bit on Thursday. Um, everybody should be kind of starting on our next 2 weeks will be over decision trees and ensemble learning. Check something real quick here. Skip something. Um, so yeah, I need to fix this. So yeah, I meant you to be working on the 11 and 12, 11 and 12 starting this week. So I had the wrong stuff on the announcement there. So anyway, yeah, we are doing decision trees and ensemble learning. I'll get started, talk about those a little bit today. Decision tree. So I'm actually going to talk about decision trees a little bit today and on Thursday. And we'll get started talking about the assignment as well. So, and yeah, again, sorry, I've had people emailing me some stuff, so I am a bit behind on some things. So, but I think in this class anyway, most everybody is in pretty good shape, and I'm not too far behind anyway on stuff. Um, so yeah, looking forward. Also, I wanted to maybe try and talk a little bit more about the class project. So I'll just remind people, keep working on that. We've effectively got 3 actual weeks face-to-face classes, and then a finals week. So we got kind of like 3 or 4 weeks, depending on how you count it. So I just wanted to give people a heads up about that as well. Start thinking about that. So that does mean that I've got quite a few things scheduled. I don't really like it like that, but we've actually got one more assignment after the assignment 6, and there is a test, and then the class project, and all those are going to be due during the finals week, basically. So I'll talk more about that, but maybe people, keep that in mind. You might want to, at least the week before, try and get the assignment done. I'll probably leave the due dates during finals week for all those, but yeah, because I know people get slammed on other courses and stuff as well. Just kind of keep that in mind that we end up having quite a few things that are going to be due for our last week of class and finals week. So. Yeah, for these next 2 weeks, we are looking at the decision trees and ensemble learning chapters from our course textbook, and have our 6th assignment on that. All right. Check one more thing here. Hopefully the link is working on the assignment 6. So yeah, I think it is. Okay. So let me bring up my notebook here. All right. Yeah. So my plan for the rest of the day on also kind of a reminder of kind of stuff. So I will probably be kind of like today, not getting in until right at 8:15. So yeah. I mean, just expect that we might be a few minutes later than what I had been at the first half of the course, getting started on stuff. So um, So our next assignment is on decision trees. I thought I'd spend probably the rest of the day, most of today, maybe some on Thursday as well, kind of going over the decision tree materials. So um, uh, so decision trees, these are another one that are relatively easy for most people to kind of understand. So another one that kind of we talked about a little bit. You should have read about the K nearest neighbors. Decision trees are also another one of those that are intuitive of a modeling method. Although actually building one, algorithmically is a little bit more complex. So you might not, if you've never thought about this, might not be able to think about an appropriate algorithm to build a decision tree. So we'll talk about the CART algorithm here. If you haven't read about this stuff in a second here, about how you actually build decision trees. But the idea is basically simple here. This notebook, make sure it's running. Yeah, so kind of remembering on this notebook, there are some stuff in here with some examples of using some methods that are given in scikit-learn for visualizing these decision trees. I thought that this image was in there. I guess it's not. I thought those images would be in the repository, but maybe not. So you might have to generate these. So yeah, a little aside on that. It looks like the notebook, at least, oh no, the notebook had a problem too, didn't it? Yeah. So if you are using the dev container environment, also, I thought that the graph biz should have been one of the things that was specified in the environment, but I don't seem to have it in my environment right now, so it must not be part of the environments file, which is not correct. So yeah, we can fix that. I'm gonna go ahead and just kind of install that by hand. I don't know if I've probably shown stuff like this before. When you're inside your containers, I mean, you do have access to the full package management for Python that's being used inside these containers. So we are using Conda. So you can do Conda installs to get stuff and manage stuff, and use the Conda from the command line. By default, this should end up going into the package that we're using, sorry, the environment that we're using. I think you have to do that root. Let's try one more time. Okay. I'll fall back to pip. So usually, if you're having problems with Conda, you will have pip installed. Pip is kind of an older package manager for Python. Not always a good idea to be using both of those at the same time, but yeah, I do think I got the thing I was missing. So yeah, if you run that notebook and you found it was missing, you probably do have to install that graph viz. I guess I didn't have that 575 environment. Okay, so yeah, I think that's working. Let's go back and try rerunning here. All right, yeah, so that's a little bit better. So it was using that library to generate the visualizations of the resulting decision trees in there. And there is another thing that you can use this tool from the command line. But you have to probably install some extra stuff. Let's check that out. So yeah, might have had the path incorrect on that, but yeah, this should actually just generate a PNG of this from this file here. So if I rerun this notebook, after it generates that, you should be able to see this. There we go. Okay. Oh yeah, I had some problem with that in the past, so I guess that's why we didn't have that in the environment. So there was a little bit of description of that. So sorry about the aside, but I usually I do, the general thing is that I've talked to you guys about, like in your class project before, that that you should try and make an effort to make sure that your notebooks are running cleanly. I try to have all these notebooks for the lecture notebooks do that, but of course things change, creep in, that have problems and stuff. So when I just tried to rerun this, I was having problems. So, but kind of like I said here in the description, you can try a conda install, but that didn't work for me. So the pip install did get the graph viz in there, and that was all we ended up needing to get those to work. Although the path was incorrect in one of those as well. So this notebook should live just one up from the top level. So you should just go up one level to go to the figures directory here. Although, yeah, another thing, okay, that's right. So yeah, this function here is supposed to be creating that file that has the resulting first decision tree that we do as an example. Okay. So let's get back to actually decision trees a bit. So this material is directly from our chapter 6 of the textbook on decision trees. The decision tree classifiers at this point in class, if you weren't familiar with the scikit-learn library before, you kind of ought to have a good handle on basically how these sort of things work. So we can use decision trees both for regression and classification. So there's also a decision tree regressor, I believe, that's probably talked about into the chapter here a little bit. But basically creating an instance of the object and then using the fit method to actually perform training or fitting. So come up with in this case, a decision tree model it's a little bit different. So it's another one that we probably wouldn't call a parameterized model. So it's not like support vector machine or linear logistic regression. So when we're fitting, but unlike the k-nearest neighbors, there is something to create the decision tree So I don't know. It's a little bit in between what I normally think of as parameterized and non-parameterized. How people would describe these kinds of things. So there is a set of models. Actually, what these visualizations represent is the set of parameters, or the tree basically was created from fitting a decision tree to a set of data there. So in this example, directly from the textbook, again, we're back to using the Irish data set, which we've used a lot. And again, in order to visualize stuff, we're only actually using two features, so the petal length and width. So let's see what happens here. So a couple of things here. There's multiple metaparameters that you can use for decision trees. The one that's probably the most common is limiting the depth. Okay, so decision trees are very prone to overfitting. In fact, if you don't specify any metaparameters here, the default behavior of a decision tree is to exactly fit the data, to perfectly classify it, which is often going to be have an overfitting problem discussed before this class previously. So the metaparameters, there's various metaparameters. An easy one to understand is max depth, which help you regularize a decision tree, help you have it stop before it's actually completely overfit on the data. So let's just jump directly to it. So a decision tree is actually a binary tree. Okay, so if you know what a type of binary tree is from a data structures class, that is what is being created when you fit a set of data to create a decision tree from it using the CART training algorithm. So and what I said, so the thing that's produced is actually easy for most people to do by hand and easy to understand. In fact, the textbook talks a little bit about white box versus black box. So unlike some of the other parameterized models we looked at in this class already, it's a lot easier to understand the resulting model that's created by a decision tree. And you can actually execute it by hand. Right. So in this case, the decision tree that we just fit decided that it's going to make its first decision based on the petal length. And if it's less than 2.45, so if it's true that the petal length for so you think of the decision tree resulting as what we would use to classify new data that we haven't seen before. So if it's less than 2.45, we'll go over this way, and if it's greater than 2.45, we'll go over here. Right? So this is a binary tree where we have leaf nodes and internal nodes. The internal nodes are where decisions are being made. Whenever you get to a leaf, that's actually, I guess, the leaf is where you come to a final decision. Internal nodes in the tree are where we're making further distinctions on. And at each step, we're doing it on only one single feature. Right? So we had two features that we fit in this example in chapter 6 here, petal length and petal width. So petal length was 2.45. We're just going to directly predict that it's cytosis. So in this case, we're doing a classification problem. This is a multi-class classification problem. There's 3 actual categories. This Irish data set, just to remind you, cytosis versus color and Virginica are the 3 types of irises. So if the petal length is bigger than that, though, we do one more test. We test on petal width. Smaller than this threshold, I'm going to make a prediction that's first color. If it's bigger than that threshold, we'll make predictions for J. So, and also to talk about these, so we'll talk a little bit about the change measurement, which is used on the CART training algorithm here. But these numbers, if they're not obvious, are for the data that we fit with. We had 150 samples that we were fitting and training with. 50 are setosa, 50 are versicolor, and 50 are virginica. So this is actually showing, and this information is what's used to calculate the Gini index here. So this is showing that by this decision, we have perfect classification, at least on the data that we trained with. We get all 50 setosas correct. We make no errors. Whereas down here, there was no actual linear decision boundary that would separate the remaining ones, as we'll see here in a second when I scroll down. So at this point, when we decide on petal width, we're close. The correct class is versicolor, and we get 49 of those. 49 versicolor have petal lengths greater than 2.45 and petal width less than 1.75. But 5 of them are actually virginica. Those 5 also had petal lengths less than 2.45 and greater than 2.45 with less than. So these ended up in the same one, but 49 were actually versicolor, which was the correct class for predicting this species. 5 were incorrectly. So, we could go further. If we change the max depth, we could make further decision boundaries to try and get that completely separated out. Right. So if you look at the decision boundaries that are made on this, do we have so I think this is the visualization of the max depth of the two tree that we had there. So we were first doing on this first one making a decision on petal length being 2.45. Do that? Yeah. So no, that's different. Let me try. I need to move this method for doing this plot here a little bit higher. Let me try. Actually, yeah, let me do that. Let's move this up to the top here. After we do this first one, let's try. Did I have that right? So I'm just trying to get this. Yeah. Maybe we have must have the labels switched here somehow. So from the visualization, we have something saying that our first decision was on the petal length of 2.45. So that looks correct, except for maybe some. I don't know why I didn't notice that before, but I guess that the this plot must be labeling those. So let's see if I can fix that. let's see, so pedal length 2.45 VN. So again, yeah, looking at this notebook, I hadn't noticed that before. So the basic idea of the decision tree is so we're limited to a max depth of two. So we're actually making two decision boundaries on the first example decision tree that we had. Right? So the first one was easy, and given, when we read about how this works, how it actually does this algorithmically to pick the parameter and the threshold for the parameter to use. But it's, I mean, there's a lot that could have been done here, right? But this is definitely a good one because this completely separates the all 50 of the Setosa from the others, right? Somewhere between approximately 2 and a little less than 3. So I can't remember exactly how the chart picks the exact threshold value. It must pick something based on, not sure what it's minimized, but yeah, I mean, this is approximately exactly in the middle between the two things that separate the Setosa from everything else. And then the other thing for the decision trees, the boundaries that are made are going to always be in line when you visualize it like this, because we're always going to be just doing a threshold on one of the features at each one of the internal nodes for the decision tree. So because of that, trying to then differentiate the rest of these, we don't have, these aren't linearly separable, the Versicolor and Virginica. Although, we could keep doing this. So later on, we'll see if we let the depth go larger, we could continue making some more decision boundaries. So, for example, maybe do another one here in order to get these two correctly classified. Keep doing stuff like that. So let's go ahead and move on. Let's look at how this card training algorithm, how it actually comes up with a decision tree when you fit a set of data like that to create a decision tree. So we're talking about how you can actually use a decision tree. So if you're handed one of those, you could easily use that to make predictions. That's kind of the white box nature of it. At each decision node, it's just a single feature. It's going to be a threshold value, true or false. And decision trees can work on categorical data, so you would have to convert it into a number again. But so if I had a feature that was true, false, or some category, it could still work on those. So I don't know if I'll go into too much detail on these measurements. There's two measurements that can be used by the card algorithm: the Gini impurity and using the and the second one. So by default, it uses this Gini here. So this is really just a measurement of, I think of it as kind of a measurement of how well the things have been separated at any given point. So just mechanically, it's a good idea to understand how you calculate this. So this is notation for how this measurement is calculated. So this is the measurement that was given in this visualization decision tree. So if you have an impurity of 0, that means that nothing was mixed. So it's completely separate. And you can get up to an impurity of Um, let's see, maximum upward. So can't really get up to 1. But the most mixed, for example, would be if I have something where I have 50, 50, and 50. I've really done no decision. I guess we can calculate what that would end up looking like. Oh, yeah, there it is. So, it'll depend on how many classes you have and what their distribution is. But like for 3 classes, if you calculate that Gini impurity, it's actually 0.66. Really nothing has been separated. So for this particular data that we're looking at, you can have decision boundaries that end up with this Gini score somewhere between 0 and 2/3. So to calculate it, it's really just this, just the sum of the squares of these ratios of the ratio of each one. So this discussion in the notebook was talking about how the Gini score for this one came out. So we've actually got 54 values that have been split into the 3 categories here. The ratios are going to be the number in each one to the total that we have. So we have 0 to 54 were in the first one, 49 to 54 were in this one, 5 to 54. So if you just take those ratios and square them and really just sum those up, sum up these ratios, and 1 minus that will give you this impurity. And intuitively, just think of this as, so the idea is that the lower that we can make this, so again, this is going to be our cost function, kind of. So the cart doesn't really uses optimization of this Gini measurement here. Right? So this is similar to the cost function we talked about before. So what cart is going to be trying to do to build a decision tree is to pick a parameter. So pick one of the features and pick a threshold on that feature in order to get the smallest Gini score possible among all possible features and all of the possible selections of thresholds on those features. So a couple other points on this. Continuing to read on down here. So when the cart algorithm is working, as long as the Gini score is above 0, you can continue to create new decisions, right? So once you reach a Gini score of 0, that means you've gotten down to a leaf node. You can't separate it any further because you've got everything all in one, whatever your number of classes are. And another thing, if I didn't mention, we are using a multi-class classification here, so decision trees work for classification problems, binary classification or multi-class classifications with any number of classes that you want to divide your data into. So yeah, just by upping the depth, we could continue on. Right, so if we make the same decision on the 2.45 for the petal length, but we weren't down to 0 yet for the other. So if we up the depth to 3, we get a further 2 more divisions that happen. So again, down here, we still haven't gone all the way down to 0 for any of these. for one of our Virginica classes here. But yeah, if we up the depth, we could continue on at least for these here that haven't separated out yet. So yeah, if you look at that, so once we have a pedal width of 1.75, we make, like, for example, just focus on this one, the pedal length. We make another decision on pedal length at 4.85. I have that right here, yeah, so that ends up being this line right here. So that separates out so getting these here, I guess. Yeah. There's it might be a little bit tough to see in this because the two decisions were made on pedal length 4.85, 4.95. Kind of stuff in here. But so let's go on to the cart then. Just bring that up. So, well, I guess well, we already mentioned white box versus black box. So textbook discusses this a little bit. It's a little bit of a fuzzy kind of notion, but yeah, decision trees are considered a little bit more understandable. At least the internals probably work in a typical parameterized model. Some people would consider them more white box, more easily viewable of how they're coming up with decisions. Yeah, another thing that I don't want to skip over this. An important thing for the kind of classifiers, we've used this previously in this class as well. So you can use these the set of where we end up at each one of these leaf nodes to give an estimate for how certain you are that if I have a new one to try to classify, how certain that it's going to be the correct class or not. So usually for something like this that has a Gini of 0, you're pretty certain, almost 100% certain that if I end up down there, probably what I'm trying to predict is very likely going to be the correct class. Whereas if you end up on nodes where things are relatively equal or have high Gini scores, your estimate of how likely you are to be correct is going to be much lower. So we can use this related to the Gini score, but we use the distribution when we get down to a leaf node, making a decision to come up with our value, our estimate of how sure we are that we have the correct class. So yeah, this is a little discussion of how scikit-learn actually returns back the probabilities for predictions that are made on the decision tree. So we end up that one node would be using that as an example. We would come up with these probabilities. 0.54, but it's TOSA. If we're down that part of the decision tree, we have 49 54 chance. Right? So these are exactly the same ratios that we use in the Gini score calculation. So you can think of these as, also as the probability that it's either that class or that class or that class at any particular point in the decision tree. Yeah, you can see exactly that. So if you pull out the, so these classifiers from scikit-learn have all of the normal. So after you fit a model to a classifier, a decision tree classifier, you can do predictions and you can do use the predict probability to get an estimate of the certainty of probability of each class. Okay, so as the final thing I'll talk about here today, kind of go over is the cart. Okay, so most students have no problem understanding kind of how a decision tree works, but actually creating a decision tree algorithmically would be tougher. It would be tougher than building a k-nearest neighbors by hand, like we talked about a little bit last week. But I already mentioned the basic idea of this. So you can think of it again as a optimization problem. Although CART doesn't do a global optimization, it does what's known as a greedy local optimization. So basically, it's going to build the decision tree incrementally, starting at the root of the decision tree and making one decision there, and then keep doing that until it gets down to a leaf node, or until we stop it for other reasons like that. So I already gave a hint on it. So like if we're using the Gini score or some other measurement, entropy is the other one I'm trying to remember. It's commonly used for this. But so if we use some measurement of how well our decisions at this point have separated the data, our goal is we want to make a new decision that leads to the lowest possible new Gini scores in this case for the resulting left and right decision tree. Okay, so so in terms of thinking of this as an optimization, we can come up with just a weighted measure, right? So if we just come up with some parameter and some threshold on that parameter, we can measure, okay, the resulting two new nodes are going to have two Gini scores, right? So this mathematical expression here is really just saying we're going to take a weighted average of these. So these are the numbers that end up being classified on the left-hand side, and these are the numbers that end up going to the right. So the true and the false, so the left and right hand decision from the tree. So we want to have a weighted average because we might make a decision where only one item goes to the left, everything else goes to the right. So in that case, it's much more important that everyone has a lot more of the resulting split than something that's making a decision that only splits off one or two things. So to be concrete, to be concrete on this, again, let's maybe go back to so what we're saying here is like for this, the root node for the decision tree that we first looked at, we decided that the best thing we could pick was the parameter petal length and the threshold. So the K is the petal length feature. That's our feature that we're going to make a decision on, and the threshold was at 2.45. So by using that, we end up splitting into one that has 50. So M for the left is 50, and it had a Gini score of 0. Right? So this is going to be 50 times 0. It's going to be 50. So 1/3 value, 50 over 150, had a Gini score of 0. And 2/3 of the value, so 100 over 50, had a Gini score of 0.5. So that weighted one would give us basically 2/3 times 5. Okay, but yeah, we've used J before, right? So this is really the decision function that we're going to be optimizing. This is really our cost function. But again, we're doing this not globally, but we're going to be making multiple of these optimizations. These are what we're going to local greedy optimizations. So I mean, it's for the same way once you define that decision function, you can't just do a straightforward optimization with it, right? So you don't have to worry about the details too much. But so basically, for the simple data where we have two features, K can either be the pedal length or the pedal width, but of course there's an infinite number of thresholds. But if you just define J like that, you don't have to try an infinite number of values. You'll be able to figure out by randomly picking a spot there and then following the gradient kind of in a similar way. But I mean, that basically means that either, so if we have these features, either pedal length and then some threshold on that, so any value from 0 to then, or pedal width could be a feature, a threshold on either. So the reason that this was chosen for the first decision is this resulting split should have had the lowest possible weighted Gini score, right, by that cost function. So if you work it out in any other split, I mean, again, you would get the same score, for example, as long as you split somewhere. So I'm not exactly certain how it ends up at like 2.5 or any value in between there, but that's kind of some details of how that works. So any split on pedal length that split all these from these 50 should end up with the same weighted average. But and then for the car, we just keep doing that until we can do it no longer, or until we have some other stop. We have depth 3. We would continue on from here to use that cost function to pick another parameter. So this presumably here, from here gives us these splits are going to be optimal in terms of the weighted combination of Gini score. And say continuing down from that. Okay, so one thing about this is maybe I might go into this a little bit more detail on Thursday. It is good to kind of understand, at a high level, that the current algorithm is the resulting decision tree is not guaranteed to be globally optimal, and unfortunately, because of the way it works, it's really important if you remember doing an algorithms course, to do a global optimization would actually be an exponential time problem. So it would be too expensive if we had a large amount of data to actually get the globally optimal decision tree. So instead, these cart algorithms just do these brutally. So these run in pretty much like linear time, close to linear time, right, like in logging time to do them node by node instead of trying to get the global optimal decision tree. And in practice, though, so it would be practical to do these globally, because it would take too much time for real data sets, and the degree algorithm is just good enough. It's usually pretty close to what you would end up getting anyway. Whereas, I guess, yeah, final thing on complexity, though, I mean, once you've made your decision tree, it is a binary tree. So if you know how binary trees work, you can make decisions on new data, so predictions on new data in logarithmic time. So it's very quick to apply, make predictions on new data once you've created a decision tree. Okay, so let me go and start. That's a good place to stop. I'll talk about a few more details on Thursday, and then maybe we'll also get into the actual things on the assignment and start talking about ensembles and things like that. So, let's see everybody. Okay, so. Okay, yep, that's it. I'll let you guys go. Let me know if people have questions. And yeah, again, sorry I'm getting a little bit behind. I'll try and get everything caught back up here if I get a chance today or tomorrow.